Let's look at the work done by a magnetic field on a moving charge. Now, I want to make it obvious before I prove it. So, as a magnetic field always acts parallel or perpendicular to the vector, to the velocity, velocity vector. Remember, if the charge is moving, say upwards or say some slant angle, and that's your magnetic field, this plane contains velocity and b, right? So this is b and this is velocity. Now, perpendicular to this plane is your force, right? So it is perpendicular. That we know of. This is a fact that we have observed. Actually, someone has observed, we have learned it. So it will or will not change the speed of the particle. Will it change the speed of the particle? Well, technically not this value, right? So it will not. Why? I can explain this with this example actually. Whenever you throw an object in the direction of horizontal, so what will the direction, how will the direction be? What will the direction of the motion or the path of the motion? It will be something like this, remember? And remember, we always told that the velocity horizontal component will not change. So this will remain same. So V1 or U is equal to V2. And that is also equal to V1. Say this point is V1. But what is changing? This will keep accelerating downwards. So remember from projectile motion. So the initial velocity, if I throw something along the horizontal, that will not change. The horizontal component will not change. But can or can't change its direction. So it won't change the speed of the particle, but it can change the direction. Right? You can see that the direction is changing over here. Same thing happens with the charge. So basically, a charge, right, moving in a magnetic field will be able to change its direction, but not its velocity. It can't increase the speed or decrease the speed. Technically, it's velocity changing. What I meant is magnitude of velocity, or the speed is not going to change. Okay, guys, let's look at the proof. Let's make it obvious. We'll make use of this fact as force because of the magnetic field is always perpendicular to the velocity. The dot product will be 0. Their dot product actually, right? The dot product between two velocities which are perpendicular will be 0. Now, force is given by substituting force, which is equal to mass into acceleration. So we have force, which is mass into acceleration, with V, which is equal to 0. Right? The right hand will continue to be 0. So we just substituted this and we got this. Now mass is mass, I can transpose it that side, or let me keep it. So mass, what is acceleration? It's the rate of change of velocity. Okay, so let me actually make the presentation. So this is, next step is, let me substitute acceleration, which is nothing but rate of change of velocity with respect to time. So your mass into dv by dt, it would be so. Agree, guys? Again, we're trying to show that the work is 0, remember. So we're going towards that energy expression basically. Now what will I do is I'll multiply and divide with 2. Can I do that? So can I rearrange m by 2, and can I take 2 of this entire expression will be what? Will be 1 plus 1. What I mean is this. And I'm using commutative law of dot product. That's equal to 0. So what did I do? I wrote 2a as a plus a. Can we do that? Right? So basically from here I have 2a, and here I have written it as a plus a. Say we have 2ab. I have written here it as ab plus ba. How can I write this? Because dot product, it obeys not like cross product. Dot product obeys commutative law. Is it not? So how will this help? This looks like your product rule. Agree? So derivative of v dot v. A particular value which dot itself will give us what? Will give us square. Is it not? So m by 2 dv square by dt, which can be further written as, actually, anyways, let me continue. This can be further written as what? d mv square by 2. mv square by 2 by dt, which is equal to 0. What is half mv square? Yes, substituting half mv square as the kinetic energy. Therefore, derivative of kinetic energy is 0. What does this imply? This implies that there's no change in kinetic energy, hence work is 0. That's all. Okay guys, this is as per product rule, and we are just taking in the constant m by 2 inside the derivative. That's it. Nothing, no fancy math is happening over there. As simple as that. Okay, so what is the conclusion? So the particle will change direction all the time. That is, it will take a circular path when it's exposed to a uniform magnetic field. So there are quite a few different cases that we'll be talking about. So let me take this case wherein the magnetic field is inwards, right? Or let me just do this. It's inwards. Then here the charge, say it's moving. Actually, I have to think of this actually. So velocity will be, this is pointing towards, no, this is pointing. I need that. It's a bit confusing, guys. I'm looking at the magnetic field which is inwards. Then I'm turning my velocity to the, okay, so bottom needs this. Okay, let me explain this, what I was trying to do. So basically, we are looking at velocity in this direction. If a particle is moving in this direction, suddenly we switch on a magnetic field, and this is perpendicular. This plane is perpendicular to magnetic field. Then it will go up, take a perfect circular motion. It'll just be in this plane itself. It won't change the plane. So let's think about it. What happens over here? We have a charge, right, moving to the right. So as per our right hand rule, so it would, our thumb will be pointing in that direction. Magnetic field is inward. So, okay, it's not a good diagram. Let me do this. How do I indicate it for you guys? So it's so, I think I got it. And the velocity is to the right. This is the velocity. That's your magnetic field inward again. So your palm will be pointing upward. Okay. So basically it would be so. If it's so, what happens? That will be your centripetal force and the particle will take this motion, this circle. If it was the other way around, actually, if it was this way, what happens is it has to take a circular motion in this way. This circle won't matter then. So I was just trying to figure out what should be the direction of the velocity. So the particle will be moving in, this is anti-clockwise. Yeah. So I was trying to figure out that. So that will be the direction of force. So what did we see? We have seen that charges, when moving, they generate magnetic field. When this charge is exposed to another magnetic field, what happens between two magnets? They push and pull, and that's what is happening over here. That push and pull is always perpendicular to the plane of the motion and the magnetic field. And with this fact, right, we are trying to prove that there's no work that the magnetic field will do on a moving charge. Basically, it won't increase its speed, but it does accelerate it. That is, it will make it go round. It will make it change directions. And that's what we are trying to prove. So I went this way. There might be other proof that you guys are okay with, but I prefer this derivation. I had few other derivations in mind, but I think this is the simplest one, which makes sense, it's very clear cut. If not, it's like it's a shortcut, which I don't want to do. This makes sense to me. So I went this way. All I did was use the dot product property, started with that. Use the definition of acceleration, then use the dot product again. And use product rule, a bit of rearrangement. And we see that kinetic energy is equal to 0. And so the work is 0. As simple as that. Okay, guys. So pause and copy everything. Don't miss anything.